Okay, so it's my pleasure to be here. A bit sad that Eva is not around, but I mean, it's a pleasure to be the closing talk of this very nice workshop. Okay, so probably some of you have already seen part of this talk because this is really a long project of mine. So the study of compatibility of quantization and reduction in the Poisson setting. So this is really a long project. So there are some news, let's say. So I'd like to give you a global perspective of this project. So let me start with something very easy, which is the reduction part. Very easy because all of you know what reduction is. So I just have to remind you a little bit my formalism, my notation, let's say. So what we have is just a Poisson manifold. And what we know is that Poisson manifold actually describe a phase space. We want to reduce it in a way that we get a smaller one. That's reduction idea. So meaning what we have is an action of a Lie group on my manifold that has to be Poisson, meaning preserving the Poisson structure. Well, we need to have some more, I would say, topological conditions like proper action, free action in a way that everything works smoothly. But anyway, beside this, let's say, technical assumptions, we want to have a Poisson action plus action allowing a momentum map, which is equivariant, meaning at the end of the story, we are able to describe the fundamental vector field of this action as a Hamiltonian vector field, where the Hamiltonian is actually given by the momentum map. Okay, so this is all we know. This is what we call Hamiltonian action. When we have such an action, what we can do is just taking the pre-image of a regular value of my momentum map and then quotient out by the action. So we have, let's say, so the quotient of C by G is actually a manifold, as I said, but it's also a Poisson manifold. Okay, so we really inherit a Poisson structure on it. And this is very nice because, as we said, this means that we can actually describe the dynamics on a smaller phase space. So we really get a reduced dynamics. So this is super nice. So that's why we would like to get something like this in the quantum setting as well. Okay, so let's say, okay, let's see. What do I mean with quantization? I would like to try first to give you a rough idea and then to enter into more technical things. So what's the idea of quantization? To me, quantization means deformation quantization. And let's say roughly the idea is the following. We have the algebra of smooth functions on my manifold, on my Poisson manifold, which is, let's say, the algebra of my physical observables. How do we describe the dynamics? We know that. I mean, we have, well, a commutative algebra, first of all. And we describe the dynamics via the Poisson structure. So we have this algebra, this is enough to describe the physics. Okay. What we would like to do is find out a new algebra, a suitable new algebra, which has to be non-commutative, because this is, let's say, the main peculiarity of quantum mechanics, which is somehow a deformation of the classical one. Okay, so this means what? Essentially means that we consider formal power series on this algebra, and we deform the product in a suitable way, again, in terms of formal power series. So we get a product, a new product, which is called star product, which is given by M, the commutative product that we have here, plus a deformation part. How did I call it? Okay, keep in mind that if we want that everything works nicely with the description, this is also called an H sometimes, these ones have to be differential operators. This is something that really comes out of the fact that you want to recover the locality of quantum mechanics, morally speaking. So these have to be differential operators. And we want this product to be associative as well. Okay, so this is the idea. Now, the question is, can I do this? Can I really cook up this passage? And then formality enters in the game. Let's see. Even bigger. Okay. Yes. Let's see. So formality theorem is a theorem by Maxim Kontsevich telling you that there is a sort of morphism. I'll try to explain you better, connecting poly-differential operators and polyvector fields. So polyvector fields on my manifold and poly-differential operators. Why this is actually related with what I was saying? It is related, and actually this proves that every Poisson manifold admits a quantization, because if you think what I had in mind before, I mean, I can somehow, how can I say, focus myself on the main objects that I have in the classical part, a B vector field, and on the quantum part, B differential operators. So if I can connect these two objects in a suitable way, then I can say, okay, this arrow, it exists, I have it. So formality does this work. So actually proves that this morphism, but I really have to explain you what kind of morphism is this. I will do that, but allows me this. Okay, so so what do I mean now with formality and reduction commute? So I have this the formality arrow here, and I have the same for the reduced manifold. Okay, now if I can cook up two vertical arrows that somehow give me a reduction scheme in terms of polyvector fields and polydifferential operators. And has to be as formality a special morphism, which is called L infinity morphism. I will explain you. Then I can study the commutativity of this diagram. So let me give you some. So probably some of you have seen in some, a couple of talks of mine, the construction of the number 2 arrow. So let's say, okay, well, I will explain you in detail. At the end, you will see that this is the number 1 is not exactly the usual formality, but is what we call equivariant version. This you will understand better when I explain you the vertical arrows. So vertical one, the vertical arrow number 2 is, as I said, a reduction scheme in terms of L infinity morphism. So this is something that this is a joint project with Jonas Schnitzer and my PhD student, Andreas Kraft, and has to be published in a Journal of Non-Commutative Geometry, I think 1 year ago or so. Number 3 is a usual formality. And number 4 is, again, a reduction scheme in terms of an L infinity morphism, but for polydifferential operators, which is a bit more involved. And also this one, this is, let's say, the new result. Okay. So this is just on archive. Okay. This one, which is, let's say, the classical side, recovers the Poisson reduction, the usual one. And this one recovers another kind of reduction scheme, which is called BRST reduction. Okay. Okay. So let's, now, if you really want to get a little bit of taste of what's happening, I really have to give you some, better idea of formality. You? Mm-hmm. This one. I don't remember. Yeah, if this, I think so. It's new even in because we had already the ideas, but I think the Cartan model was not clear yet in the thesis, if I remember correctly. Okay. So a little bit of tasting. You really have to catch a little bit of what an L infinity algebra is, what L infinity morphism is, and that's essentially enough for getting the idea. So L infinity algebra is a pair, which is consisting essentially of, we need a graded vector space. You always have a shift by 1 because you have to make everything coherent, but okay, it's a graded vector space. And then this generates a symmetric algebra. Sorry, coalgebra. So, well, co-freely co-generated by L. And then you have a codifferential. Okay, to me, degree 1. To me, if you really want to understand this object, the easiest way is to think of L infinity algebras as Lie algebra up to homotopy, meaning what? So this is L infinity. Because essentially what you can have is the ingredient of the codifferential is contained in a sequence of maps. So you have, let's say, n maps, Qn, from and then we have, yeah, by 1. So these are really these are really structures that you can really see there are Lie up to homotopy, in the sense that you have, for example, a proto-example is a differential graded Lie algebra, meaning exactly this. You have a graded vector space, and then you have a differential, meaning n equal to 1. Then you have a Lie algebra structure, meaning n equal 2, and that's it in this case. In general, you can have much more. Okay. Another case, which is of some interest for us, is what we call curved DGLA. So here you have graded vector space, differential, and Lie bracket, and that's it. Curved means that you always also have acute 0. But then all the rest are 0. So you see, you really have some extra structure which have to be compatible with each other, of course. But to me, I mean, this is the easiest way to understand this L infinity structure. And then you can ask, of course, you can ask, what is a morphism of this object? So imagine you have 2 L infinity algebras. So morphism between them means, of course, that it commutes with respect to the codifferentials. It preserves the codifferential. So also in this case, you can, are, yeah, very particular case, because you have not n maps, but only 1, 2 maps. And here you have 3, but you can have much more. Also in the case of morphism, you can, let's say, adopt the point of view of coalgebras, let's say, so this more abstract, and say, okay, this is just a morphism that connects these 2 objects. Or you can say, okay, this is actually uniquely determined by a sequence of maps, again, N1. I always forget the shifting. Yeah. Okay, and of course, this has to connect piece by piece the structures, but you understand, I mean, in this case, for example, you have to connect D and D with the second one, and vice versa. So you really have all the possible shuffling you can imagine. Okay, so Another important ingredient here is the concept of L-infinity quasi-isomorphism. Means that F1 is an isomorphism in cohomology. Okay. Because you have the complex out of the DGLA, let's say, structure. Okay, so now, so this is super abstract. Now I want to show you what L-infinity structures do we have. So first of all, as I said, we have polyvector fields. So polyvector fields means, let me put a bullet here. You have sections on your tangent bundle, 0 as a differential, and then you have the Schouten bracket. Okay, it's a DGLA, so you can interpret it as a L-infinity algebra. Okay, so far so good. What is important here? The important thing is that whenever you have the DGLA, for example, you have a Maurer-Cartan equation. I don't know. Okay, and if you see, if you look at these structures now here, what you have as a Maurer-Cartan element is just a Poisson structure because D is 0. So you have the Schouten bracket. So what you get here is exactly a Poisson structure. So second one is the poly, so the poly differential operators. So how do we get there, let's say? So we start with an algebra, associative. And in our case, A is C infinity of M. Then what we take is the Hochschild cochains on this. Means simply homomorphisms from A. Yeah, let me fix an N here. Okay. So you take these chains, these cochains, sorry, and then you can define a DGLA structure as well. So let me start with the bracket. The bracket is what we call Gerstenhaber bracket. Okay, I don't want to enter too much into the technical details. Think that this object is a graded commutator with respect to a product, which is simply a concatenation of homomorphisms. Okay, that's it. So you can just, really concatenate morphism. This really defines a product on that. And then you consider a graded commutator with respect to this. And this is a Lie bracket. And this is the one you want. And why this is nice, also here, if I want to study now the associativity of a product on A, I can reformulate it. So this is, let's say, an observation in terms of this algebraic structure. So associativity of a product M means this, can be rewritten in this way. Okay, we need also a differential. This is called the Hochschild differential, and this is defined in this way. So out of the Gerstenhaber bracket. Okay, also at this level, we want to see now what are the Morer-Cartan elements. Mm-hmm. Sorry, say again. In the general case, well, I mean, this always has some, I would say, some interpretation. So they are important elements in the DGLA in general, and they always, I mean, if you study, you can study deformation theory of many objects, and in many cases, let's say there is a differential graded Lie algebra that describes the deformation, and the Morer-Cartan elements are the ones that you want. They are really the key points to describe the deformation. Okay. Okay, so in this particular case, Morer-Cartan elements can be seen in this way. So you have your product, then you take an object which is, as usual, in the Morer-Cartan elements are in the first one, in the first n. So this object is a Morer-Cartan element if and only if I take my product and I add this part, this is associative. So this is Morer-Cartan if and only if this is an associative product. So this we can now connect with what we said here. Because, okay, I mean, I'm not talking yet of formal power series, but morally speaking, what I'm doing is taking a product and adding a part here, which is exactly, you will see that this is exactly this part. And I want to study in which condition now the deformed product is associative. When the piece that I add is actually a Morer-Cartan element. So this is important to understand because it means essentially that if we want to construct this arrow, we are looking for a morphism connecting dipoli and what I didn't write it yet, dipoli. Okay, so this graded vector space with this structure. So I want to construct a morphism that takes dipoli and gives me dipoli, but that preserves the Morer-Cartan elements, because I want to go from Poisson structure, which is the Morer-Cartan element here, to an associative deformed product, which is a Morer-Cartan element essentially there in the polydifferential operator part. I mean, I'm cheating, of course, a little bit because, okay, we have to take care of the fact that I really want to have something in terms of formal power series, but believe me that this is not the hard part of the story. So really the hard part is to construct the morphism, an L infinity morphism from dipoli to dipoli, and then you can essentially extend by linearity to formal power series and you have what you want. Essentially, yeah, okay. Okay. So now let me really go. So I want to try to explain you first the second arrow, well, they are both very technical, but this is a bit less technical than this one. And the strategy is really similar. So at least you have an idea. Then I can comment more on the last one, if I have time, I hope so. But I mean, at least you have an idea on how to construct this. Okay. So what's the idea? The idea is first that I want to describe, how can I say? I would like to cook up a DGLA which is what we call equivariant multivector field, whose Morer-Cartan element are not just Poisson structure, but are Hamiltonian actions, essentially. So I really want to encode the information of the Hamiltonian action in terms of a DGLA. So let's see how. Yeah, here it is. So the vertical one, I have to clarify, as I'm trying to say that the upper part is not exactly, is not only T-poly, there is something more that I have to clarify. The classical one. Okay, so you will see what I mean. Okay, so I want to encode the information, because remember what I want to do. I want to rewrite, somehow rephrase reduction, the classical reduction, in terms of this arrow. So I have to start with the correct DGLA on the top. Okay, so how do I do that? So I define another graded vector space as follows. Let me write, and then I try to explain properly. Okay, why do I do that? So think to this object in the following terms. These are essentially polynomial maps from G to T-poly. So this is just another way to rewrite that we are considering all the polynomial maps from G to TK. And this is good because, well, of course, this is now a DGLA, but very similar to the one we started with, so T-poly. So the differential is still 0. The bracket is essentially given by the bracket we had, because I just have to evaluate. I call it so this is the element in the Lie algebra. So I just have to evaluate. So you see now these are polyvector fields, and this is the Schouten bracket. So it's just, yeah, a rephrasing. What is new here, and this is really important because remember that we want to encode not just the invariance of the action. We want to encode the fact that we have a momentum map inside this DGLA. We have a curvature. Okay, a curvature means, you remember that we have a zero part here. And this is exactly this map, but T0 poly just means functions. Okay, so this is exactly the momentum map. What is nice to see, what time is it? So just to see how much time do I have? I don't remember when we started. Half an hour, okay, great. So then what you can see is really why I say that this DGLA encodes the information of Hamiltonian action. Because now, if I want to look at Morer-Cartan elements, the Morer-Cartan equation has the curvature as well. So the Morer-Cartan equation is this one. Okay, because D is 0, so we don't have it. Okay. So if I look at P, I split in the 0 and the 1 part, so the function and the B differential operator part. Then I just have to substitute here. So this is the definition that I'm using. So I have this is Poisson, so it goes to 0. Then I have pi and j. J and j, again, it goes to 0 because this is an equivariant one. And this is equal to lambda xi. So at the end, you see what I have is, did I write it correctly? Yes. Xim, which is this one, the fundamental vector field, equal to this one. The other way around, sorry. I say the other way around. So you see, I'm saying that that having a Morer-Cartan element means exactly what we want, encodes the whole information of Hamiltonian action. Okay, so this is the DGLA that we want to study. And now this means that I have to reformulate a little bit. This arrow is not exactly this arrow anymore, but lambda is the curvature, which is this polynomial map that gives you the momentum map. So from G to T0. So this is the curvature that I am injecting in the DGLA structure. Okay, it's a central element. No, this is let's say the co-momentum map. This is because I gave you this and J psi. Sorry, can you see? You see? Sorry, yeah, it's the dual version. I don't know how to say. Yeah, exactly. Yeah, thanks for the. Okay. So now when the polyvector field is not when the bivector field is not Poisson, you mean? Exactly. 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 So it's really counting the degrees, and they cannot, yeah. So to me, really now, getting a reduction scheme in terms of these objects means cooking up an L infinity morphism among these two DGLAs. So this is what we want to do. Okay, and now I really want to try to show you how. So of course, well, it has to be an L infinity morphism because I want to preserve the Morel-Cartan elements. And I also want to somehow take care of the curvature. So this we have to somehow keep in mind. Okay. So how to do that? So the idea is the following. So let me first, well, give you a very, very rough idea. So the idea is that we find two objects which are connected via L infinity morphisms to those ones in this way. So that, I mean, I need to, of course, to get that this is also a quasi-isomorphism. Quasi-isomorphism also means that you can actually invert it as an isomorphism. I mean, let's say, in general, when you have an L infinity quasi-isomorphism, you know that the inverse exists. You cannot write it explicitly, but in this case, we could write it as really an explicit formula. So we could invert this. What am I saying? Let me see. No, sorry. This is not the one we have to invert. This is the one we have to invert. So we, yeah. So what you do at the end is composing these arrows and getting the morphism that you want. So I have really now to try to give you an idea of what these two objects are. Okay, so the first one is rather easy and is called T because it's essentially a Taylor expansion. So what's the idea? The idea is that in general, you can look at your manifold in these terms as C. Remember, C was the pre-image of the regular value of zero of the momentum map cross G star. I mean, of course, this is not always true, but in the case in which we are, we have a proper action, you can essentially always do this assumption. It's not that strong. And then you really expand Taylor-wise. So you really go in the two directions. So you get the following map. Mhm. So this is really a Taylor expansion in the sense that you really have the Taylor coefficients at the end. So what we could prove is that there is actually such a morphism. And this is, as I said, let's say the easy part, because if you really look at the formulas, this is really nothing more than Taylor expansion. But now you have to try to get from here to there. And this is, let's say, the more complicated part, where you need to, you need to use some more technologies. Yeah. Symmetric algebra, symmetric and anti-symmetric. Now, just for you to have an idea of what is this object, well, there are two things I can say. First, I can refer to the Cartan. I mean, we give this name, the Cartan model, because if you study the diagram of quantization and the reduction in the symplectic case, this is really proven by using a Cartan model, which is very easy to understand, actually. So what do we have? Classically speaking. So reduction is what? You have your manifold, sorry, the contrary. You have your manifold, your constraint surface, right? Which is inside that. And then you can project on the quotient. So in the symplectic case, it has been showed essentially that you can take this diagram, pull it back to forms. This is not M. And this is exactly what we call Cartan model for the equivariant de Rham cohomology. So using this diagram, let's say, it has been proved that quantization and reduction commute in the symplectic case. In our case, we cannot use this because if you don't work with forms, but you work with vector fields or polyvector fields, you don't have the pullback. So the situation is more complicated, but still we wanted more or less to use this philosophy. So the idea is that, okay, how can we find a suitable model that makes this job? And the idea was, well, we simply compute the cohomology. So you compute now the cohomology. Of the Taylor expansion. And you really get what you want. You really get something like, what was the name? Yeah. the very same. So this is actually now your P, and this is now your E. You have to be a little bit careful because, okay, I mean, you compute the cohomology and you have, let's say, the graded vector space, which is your model. And then you have to be careful with the structures because they have to adjust in a way that these are actually preserved by these arrows. This is, let's say, the more complicated and technical part. But okay, I mean, trust me, you can do that. So you can, once you compute the cohomology, you have your graded vector space, and then you can adjust the differentials in particular in a way that these are more the morphism that you want. And then you have your reduction scheme. So you actually compose and you have your reduction scheme. Okay, so this is more or less the story of the classical part. How much time do I have now? 10 minutes, good. Okay, so I just want to give some last comments on the fourth arrow now, because the fourth arrow essentially follows the very same line. So what I have to do is, first of all, let's say, try to fix what DGLA I want to start with. Then I have to try to cook up this arrow. And the way I cook up this arrow is really the same as we did here. So really Taylor expansion Cartan model. Then the problem in that case, when you work with the polydifferential operators, is that adjusting of the structures is way more involved. But okay, so I just want to give you an idea of the ingredients. Yeah. Mm-hmm. No, it's not unique. It's so everything is up to homotopy. I mean, it's unique up to homotopy. Yes, yeah. Yeah. It's Rico, yeah. Okay, so now, so I mean, morally speaking, you have to imagine that you have this diagram is divided in two. I mean, the left part is the classical and the right one is the quantum part. Okay, so what do I want here? I want to have again something more. I mean, I just there I started with a Poisson structure, which was G invariant and allowing a momentum map. So there I have, let's say, the star product, the deformed product, but has to be more than this, has to be what we call equivariant star product. The very same, G invariant plus allowing a momentum map, which is now a quantum momentum map. Let me call it H. That now takes my Lie algebra and that ends up in formal power series. So meaning you have something of this shape where J1 is the classical one. Okay, so this is what I mentioned before. If you want to now to reduce equivariant star products, So really go from, let's say, equivariant star product to me means star product, I mean, let's say compatible with our quantum momentum map. And then you want to go to a reduced one, just means a star product on the reduced manifold. So this is the reduction scheme, which is called BRST. And this has been studied by Bordemann, Herbing, and Waldman. I don't remember, 2001, if I remember correctly. So what we want to do here is now try to reproduce this reduction scheme in terms, well, recover this reduction scheme in terms of L-infinity morphism. This is something from physics. This is these are names. Okay, these are 4 names, and this comes out of a theoretical physics theory, actually. Okay, so the very same, just to show you what are the ingredients. So what I want now, I want a DGLA whose Morer-Cartan elements are equivariant star products. Okay, so again, let me skip the formal power series part, because this is just, let's say, the extension. But so, same idea. As before. So polynomial maps from G to D poly. And then I have to construct the DGLA structure. I mean, I don't want to write everything. The bracket is again easy extension of the bracket that we had here of the Gerstenhaber bracket. So in the very same spirit of the poly vector field part. And also the differential is really an easy extension. But what, again, we have to keep in mind is that we want to add a curvature to this DGLA, and this curvature has to somehow encode the Hamiltonian part. So the momentum map. And in this case, is simply the leaf derivative along the fundamental vector field. So this is now what we call equivariant polydifferential operator, DGLA. And as I did before, now you can take this DGLA structure involving the curvature as well, compute the curved Morer-Cartan elements, and you can see that they really give you back the star product allowing a quantum momentum map, so the equivariant star product. So you really describing the Hamiltonianity of the quantum setting, let's say, in a DGLA. Okay. And then we have to do exactly the same as we did here. So we have to cook up this arrow. And I don't want to be too technical here, but I can tell you that, as I say, the Taylor part is very easy, the very same. The problematic part is the Cartan model, more complicated in this case, second case, because when you really have to adjust the structure in a way that these arrows preserve the structure, you have to, well, this is a bit more involved, you have to work more. But anyway, this still work. And I had a comment in mind. What did I want to say? Okay, doesn't matter. And at the end of the story, what you have, yes, and also as we were discussing before. In this case, at the end, we get an arrow that recovers the Poisson reduction. In the new case, we get an arrow that recovers the BRST reduction. So really redescribe, let's say, as we can say it's a generalization of BRST reduction in L infinity terms. So end of the story, we have the two vertical arrows. We have this arrow because this is the formality for this Poisson manifold. We don't have yet the first one because now you understand that here we have the equivariant one. So we still have to cook up the equivariant version of formality. At some point we thought we had it, but then we discovered that the curvature was giving us a problem actually. Yeah, because you really want to cook up an L infinity quasi-isomorphism that it's curved and preserves the curvature. Otherwise, this doesn't work. So at the moment, we are still working on this one. So we are working, this is a joint project with the people who created this conjecture. So Richard Nest, Boris Tsigan, plus Andreas and Jonas as well. So I hope for next Poisson geometry conference, I can tell you finally after many years if this diagram commutes or not. Okay, I'll stop here.
So before you put the red stuff, the T-poly is the cohomology of T-poly.
Exactly, yeah. That's why it's called formality, yeah.
This equivariant thing is complicated, but it's probably a multiple. Is it true also that this way taking homology from D to T?
From D to T, I don't know actually. I don't know.
Because could it be that one would think that there is this master thing that has all these ratings and so on, and the different directions are attained by taking homology, and then the formality comes from some.
I mean, I would say very much yes as an intuition. Yeah, so that's a bit the direction we tried essentially. And we also figured out how powerful is homotopy transfer. For example, I mean, for the D-poly part, we had to use it a lot, homotopy transfer theorem, to deform the retracts that we get and go and get the correct structures. So pretty much yes, but yeah, we are still not, I mean, we have some new ideas. I mean, at the moment, we are really working a bit on the operatic formulation of formality and the G infinity formulation of formality, because apparently, I mean, the G structure is, let's say, the tricky one when you want to connect the curvatures, but still not able yet.
In some cases, on the left side, I know that there is a probably equivalent formulation without curvature, in the sense that so what you do is cut this kind of Gaussian bracket, and then you find the BRC charge.
Yeah, exactly.
It has no curvature. I don't know, maybe it's just.
Maybe yes, I don't know. I don't know. Yeah, I don't know. Might be. They said I have no idea.
even in the Poisson which is not known.
No, in the symplectic case, it is. It is known. In the Poisson, not. No. I mean, this is a way to solve it, let's say. Yeah, this is a way to solve it. Yeah, yeah. In the symplectic case, this has been proved that they commute. So that quantization and reduction commute. Well, yeah, let's say so. Yeah, let's say automatically. Yeah.
Okay, well, let's thank Chiara again.
Thanks.